And we are now recording, so let's get the chair set up for the whiteboard. And let me get things organized here. First thing I'm going to do is shove James up against the wall here. Alright, you can't see this, and then we'll get this taskbar up out of the way as much as possible. And then we'll do this taskbar down here as much out of the way as is possible. Okay. And finally, move the whiteboard over as much as I can to get maximum white space. Okay, I think that's about the best I can do. Okay. All right. Now, one last time, any questions, thoughts, concerns, issues before we get started where we left off last time? Okay, last time we did leave off Chapter 1, Systems of Linear Equations. Sorry if I sound all clogged up, I am. And we're in section 1.3, Applications of Systems of Linear Equations. And we sort of glanced through some least squareds, polynomial fits, those kind of things. Those take a lot of time to do. If you need them, you know where to find them. There they are. But this network analysis is something that you use a lot in several fields of engineering, so I thought this would be worthwhile doing. And that's where we start today on page 29, example 5, analysis of a network. And here's the first network they show. All right. Now, different books use different terminology. I like to call these nodes. I can't remember what this one calls it. Junctions. In Kirchhoff's laws, they're called junctions. So, but this isn't electrical right now. It's just any kind of a network. There is node 1 or junction 1. Over here will be node 2 or junction 2. Okay. Down here will be node 3 or junction 3. And down here will be node 4 or junction 4. And over here node 5 or junction 5. Okay, we have communication links between all these junctions. My drawing leaves a lot to be desired, but you get the general idea. Now, we know that going from 2 to 1, we have 20 whatevers, okay? 20 are heading in that direction. Leaving 1 going down to 4 will be an unknown number, and we'll call that x sub 1. Leaving 1 and going down toward 3 is an unknown number that we'll call x sub 2. Leaving 2 heading down toward 3, we have an unknown number, and that we'll call x sub 3. Leaving 5 going up to 2, we have an unknown number. We're going to call x sub 4. Leaving 3 heading toward 4, we have a known number. That will be 10. And leaving 3 heading toward 5, we have another known number. That will be 10. And then leaving 4 heading toward 5, there's our x sub 5. Now, here are the rules for a network. Okay? At any junction or node, you can't pile up or be deficit. Everything has the balance. So in other words, if I could get my pen to show up, there it is. At junction 1, you have the same number coming in as you have going out. It must be that way. Okay? You can't collect and store them at a junction. Okay? So we can start writing down some equations from that. So we know leaving 1, junction 1 or node 1 here, my pen is, there it is x1 and x2 are leaving. Those are both leaving. We know that 20 is coming in, so from here x1 plus x2 has to equal 20. So there's our first equation. X sub 1 plus x sub 2 is equal to 20. Okay? There we've taken care of node 1 or junction 1. Let's go to junction 2 over here. We know that x3 is leaving, x4 is coming in, so the amount coming in has, and 20 are going out, the amount coming in has to equal to the sum of those going out. Now this is going to be a little bit more of a problem, because here's what I would say. I would say x of 4 coming in, and it doesn't matter which one you count, is equal to the ones going out. That would be 20 plus x sub 3. But guess what? I don't want my variable on this side. I want to subtract the x sub 3 from both sides. So this goes to 0, and then we'll have a minus x sub 3 here plus x sub 4. So there's our second equation. Now you could do it any way. You could have said x sub 3 minus x sub 4 is equal to minus 20. That works just as well. Okay? However you put them together, that's what it needs to be. Okay, let's go to junction 3. We got 2 coming in, x sub 2 plus x sub 3, 2 going out, 10 plus 10. Those have to equal, so x sub 2 plus x sub 3 is also equal to 20. Okay, now don't confuse that. That 20 is because 10 plus 10 is 20. Okay, let's move down to junction 4. You got x sub 1 coming in, x sub 10 coming in, and x sub 5 leaving. So again, I think what I would do is x sub 5 is equal to the sum of these two. So let's put the x sub 5 here. And you can do it any way you want to. You decide. Is equal to x sub 1, or let's make it 10 plus x sub 1. But I don't want the x sub 1 over here, so let's subtract it out of here, minus x sub 1, and put it over here, minus x sub 1. And then these two add to 0. So the fourth junction is minus x sub 1 plus x sub 5 is equal to 10. And then the fifth junction down here, you got 2 coming in and 1 going out. So again, I think I'll do the going out here. X sub 4 is equal to 10 plus x sub 5 coming in. 10 plus x sub 5 is equal to, but I don't want the x sub 5 here, so I'm going to subtract it away here. And subtract an x sub 5 here. Alright, there's our system of equations. Okay, now I've tried to put variable under variable, equal under equal, and number under number. Okay, it's a little messy now. Let's write it as a matrix, and I think things will look a little bit better. The first one is a 1, 1, 0, 0, 0, 20. Augmented matrix. Now, if it's okay with you, I'm going to go on and swap these two rows because I know I want a 1 next. So let's do that. So this is going to be a 0, 1, 1, 0, 0, 20. Okay. Now we swap these two, so the next one's going to be a 0, 0, minus 1. Somewhere here, here it is. 0, 0, minus 1. 1, 20. 0, 20. Now, I can tell you right now, I want that to be a plus 1. So I'm going to change that to plus 1, make this a minus 1, and make that a minus 20. Okay, because I know I want that one to be a leading 1. Okay. Fourth one, a minus 1, and then 3 zeros, x of 2, x of 3, x of 4, 1, and this will be a 10. And the last one is a 0, 0, 0, 1, minus 1, 10. Okay. Now, I'm going to rewrite that matrix. I wish I had looked ahead enough to do it. I want to swap these two rows too. And you see why? Because I want that leading one here to be a plus 1 as well. So let's move this down here. Okay. 1, 1, 0, 0, 0, 20. 0, 1, 1, 0, 0, 20. 0, 0, 1, minus 1, 0, minus 20. Now, my new fourth row is this one. 0, 0, 0, 1, minus 1, 10. Now, before I do the new fifth row, I want this to be a 0 here, right? Right here, but now it's in the fifth row. So I'm going to add row 2 to my new row 5 and get what it is. So row 2 plus row 5. Row 1 plus row 5. That's once it's moved to row 5. So 1 minus 1 is 0. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 1 is 1. No, I'm not over. No, 0 plus 0 is 0. That's another 0 there. And this is a 0 plus 1 is 1. And 20 plus 10 is 30. Okay, now I'm skipping steps like crazy. I hope you're following what I'm doing. But we are so close to being row echelon form, it's pathetic. What we want is this one to become a 0. So what we're going to have to do there is minus row 2 plus row 5, and that becomes a new row 5. Now, I don't know if I can get it all in here, but I'm going to try. Okay, it's going to be a 1, 1, 0, 0, 0, 20. 0, 1, 1, 0, 0, 20. 0, 0, 1, minus 1, 0, minus 20. 0, 0, 0, 1, minus 1, 10. Just barely going to make it, I think. And this one, when you do minus row 2 plus row 5, that will be a 0 here. Minus 1 plus 1 is 0. Minus 1 plus 0 is minus 1. 0 plus 0 is 0. And 0 plus 1 is 1. And minus 20 plus 30 is 10. Okay. For some reason things look strange down there. I don't know why. There's some sort of symbol there at the bottom. Okay, I can't quite close out my bracket, I don't think, but you have the general idea that there is, come on, where did the pen go? There it is, it keeps moving. Okay, closing this out there. I don't know what that is in the corner, but it's sort of blocking my view. All right, now I think I'm going to have to get rid of my equations up here. I just don't have room for everything. So what I'm going to do is get the eraser to erase. Okay, so I hope I won't need these again. I hope y'all have been watching and making sure I didn't make a dumb mistake. If you didn't, it's your fault, not mine. Okay, no, I'm just kidding. Okay, I think we'll be able to come back and use our drawing to check our work. Okay, now let's go back to our draw. Okay, the next matrix up here. Alright, what do we want to happen next? Let's review. I should have been doing this all along. We want 1 here, 0 is below it, we got it. Leading 1 here, 0 is below it, we got it. Now, what we could be doing, and maybe we should, is do Gauss-Jordan elimination. I was just as okay doing Gaussian elimination, but let's go on and do Gauss-Jordan since we're here. It's easy enough. So what we'll do here is we want to eliminate this 1 and make it go to 0. I don't think I want to do this. Let's just do Gaussian elimination. Okay, we got 1 here, 0 is below it, 1 here, 0 is below it. 1 here, we got 1 0 below it by adding these two rows, so this is going to be row 3 plus row 5. Row 3 plus row 5 will be the new row 5. Oh, here's Jesus. I don't know how long he was sitting there, but let's get him in the class. Okay. I hope that's Jesus walking in right there that I hear. Yeah, good deal. All right, got you in. Perfect attendance again today. Way to go, folks. Okay. Now, what we're doing is example 5, chapter 1, Systems of Linear Equations, 1.3, Applications of Systems of Linear Equations. Example 5 starts in the middle of page 29. We have progressed down the page for quite a ways here. What they do in the book is write the augmented matrix and then magically write the Gauss-Jordan elimination. Okay, we're actually eliminating, but I chose not to do Gauss-Jordan, but just do Gaussian elimination. So what we're, yes, I'm recording the class. I don't know if you can see it, but it's down here in the lower right corner. Can you see that little red symbol there? Okay, that means we're recording. We're 20 minutes into the class, okay, into the recording. Okay, so yeah, it will be recorded, but that reminds me, remember to remind me at the end of class to stop the recording, because I did it once last week or week before I guess it was. I forgot to stop this class, went on, ate lunch, came back, started teaching my next class. I said, did I start the recording? I went down and checked it. Yep, it's recording. I don't remember doing it, but well, I hadn't. That was still the recording from your class. So your class for that week actually says Physical Science 111. Don't pay attention to that part. The first hour and 15 minutes are your class approximately. And I have to tell them they have to ignore the first hour and 45 minutes because I had 30-minute lunch in there. Ignore that and start, between an hour and 45 minutes, or around the hour 45 minutes into the recording. That's where their class picked up. So it's a mess, but you can do it. You're welcome to listen to the physical science if you want. Okay, so here's where we were. We got this far. We got 1 here, zeros below it. Oh, leading 1 here, zeros below it. Leading 1 here. We're trying to get a 0 below it, so we did row 3 plus row 5, trying to get this to go to 0. So let's do it. Let's write down equation, or row 1. 1, 1, 0, 0, 0, 20. Row 2 we're leaving alone. 0, 1, 1, 0, 0, 20. Row 3 we're using, so leave that alone. 0, 0, 1, negative 1, 0, minus 20. Row 4, leave that alone. 0, 0, 0, 1, minus 1, 10. And the new row 5 is going to be row 3 plus row 5. That would be 0 plus 0 is 0. 0 plus 0 is 0. 1 minus 1 is 0. Minus 1 plus 0 is minus 1. 0 plus 1 is 1. And minus 20 plus 10 is minus 10. Okay, now we've got one more to eliminate, this one right here. So this will be row 4 plus row 5 is the new row 5. Alright, so let's squeeze that one in here. Isn't it so much easier to just write down the answer like the book did? Shame, shame. Yuck. Okay. First row we're leaving alone. 1, 1, 0. I don't know if you can see those things when they pop up there. It's because I'm left-handed. My hand rests on some crazy buttons that are at the top of this screen, this pad. I don't know what they do. They just get in my way. 0, 0, 20. Okay. Second row, 0, 1, 1, 0, 0, 20. Third row, 0, 0, 0, no, 0, 0, 1, sorry about that. Minus 1, 0, minus 20. Fourth row, 0, 0, 0, 1, minus 1, 10. And then what we get when we add row 4 to row 5, that would be a 0. That would be a 0. That would be a 0. 1 minus 1 is a 0. Uh-oh, I think I've messed something up. Maybe not. No, I did it right. Good deal. Whew. Well, not quite. Oh, no. They're in reduced row echelon form. I'm in row echelon form, but we do wind up with a row of zeros at the bottom. Now that means something. It means we have an infinite number of solutions. So we have to start figuring out what those are. Well, the only column that you have that does not have a leading 1 is the 5th column. So evidently the x5 is arbitrary. So we'll write that down. X sub 5, and their favorite arbitrary variable is t. Okay, from this one, this says that x sub 4 minus t is equal to 10. So that means x sub 4 is equal to t plus 10. Okay. This one says that x sub 3 minus t minus 10, let me write that down, x sub 3, this is the third row here, minus the x sub 4, which will be a minus t minus 10, is equal to minus 20. Okay, and if you added this to both sides, you get x sub 3 is equal to t minus 10. Okay, that's a 3, not a 2. I don't know where the 2 came from. X sub 3 is equal to that. Then going up here, you have x sub 2 plus x sub 3, so that would be plus t minus 10 is equal to 20. That's what you get from this row. Okay, well, let's add 10 to both sides and subtract t, and you get x sub 2 is equal to 10 minus t. And then find your x sub 1 plus this x sub 2, which is plus 10 minus t, we know is equal to 20. And if you subtract 10 from both sides, I'm sorry, I messed this up. This is a 30 here because you added 10 to both sides and subtracted t. Sorry about that. I hope I haven't done anything else stupid like that. So this is a 30 here. So you're going to subtract 30 and add t, so you have x sub 1 is equal to t minus 10. Now, I just noted that if you added t1 or x1 plus x2, you got 20, and x2 plus x3, you got 20. So that means x1 minus x3 had to be 0, so that means x1 is equal x3, and sure enough it is. Okay, so I don't have much room, but I'm going to write it down as an ordered quintuplet here. The x of 1 is t minus 10, x of 2 is 30 minus t, x sub 3 is t minus 10, X sub 4 is t plus 10. And x sub 5 is t. So for any value t, this should work. So let's take the easy one, t is equal to 0. Well, that's saying that this one's actually heading in the wrong direction. It should be heading north here and be 10 degrees going to 1. X sub 2 would be 30. 30 leaving. You have 20 coming in, 10 coming in, and sure enough, that's 30 going out. So that works. Okay. X sub 3 over here was t minus 10, so that's a minus 10. So turn this around, have this going 10 into here. X sub 4 was 10 coming in here, you got 20 going out, so that works. X sub 3 had 30 coming in here, 10 going away, 10 going away, and 10 going away, 30 leaving, 30 coming in. That works. X down here at node 4, you had 10 going out, 10 coming in, those add to 0, and t was 0 here, so 0 is equal to 0. That works. And over here coming into 5, you would have had x sub 4 was 10 going out, 10 coming in, that's 0, and this is 0. Yeah, they work. Now, if you don't like having to change directions, let's find some value t that might work otherwise, like 10. Then this would be 0, 20, 0, 20, 10. Okay? And unfortunately, you're not ever going to wind up with one that out of 0 in it, I don't think, or a negative number. If t was equal to 20, this would be 10, 10, 10. Oh, that would work. 20 and 20. No, wait. What did I say? T equal 20. That would be 10, 10, 10, 30, 20. So that would be, to have them going in the right direction, that would be one possible solution. Okay? But what they did it just like we did. X sub 1 is t minus 10. X sub 2 is, I put 30 minus t, they put minus t plus 30. X sub 3 is t minus 10. X sub 4 is t plus 10. And x sub 5 is t. Okay? Infinitely many solutions. Okay. And then they picked t equal 10 and showed what they got. Okay. Now, any questions on that before we leave it? Pretty simple problem in that I had only 1s and minus 1s as your coefficients, and either zeros, well, plus or minus 10, plus or minus 20 as your constants. But you still had a lot of little steps, and that was a problem with linear algebra. You kept repeating the same things over and over again and came up with it. Now, they did Gauss-Jordan elimination but didn't show all the steps. If you had shown all the steps, it would have been close to twice as long a problem. But then you wouldn't have had to do the back substitution like we did here, but it all worked out the same. Now, excuse me just a moment. Like I said, my head is clogging up. I think it's from too much grass pollen or something from the mowing and stuff I did. Okay. Now, any questions on example 5? All right. Now, my question to you, I think I've asked it before, but just remind me. Have all three of you had Physics 214, or are some of you in Physics 214 this term? Last summer. Okay, so James has already had it. How about Kira and Jesus? Have you already finished your 214 physics, or are you in it now? Kira, Jesus. I don't remember. James, do you remember if they finished? Were they in it with you last summer? I know it's virtual and you don't really get to know your classmates, but both of them were? Oh, okay. Well, I don't know. So I'll assume that you don't know. Okay. So what I'll do, are there any reasons to keep this on the screen any longer, or can I clear it? I don't hear any objections, so I'm going to clear it. All right. I'm right now going to type out for you Kirchhoff's laws. This is a deal. It's sort of a network analysis, but this is electrical network, not just any old network. The other could have been a transportation network. It could have been an information network. It could have been any kind of thing like that. This is electrical circuits. Let me type out for you Kirchhoff's two laws. Okay. Now they use the term junction where I was using node sometime. All the current flowing into a junction must flow out of it. Okay, there's Kirchhoff's first law. That's often called the junction rule. Okay, all the current flowing into a junction must flow out of it. Okay, done. Here's the second of his laws. Okay, the sum of the products IR, where I is current and R is resistance, around a closed path is equal to the total voltage in the path. All right. Now that's worded as a mathematician would probably word it. Okay. I think writing it in sort of physics terms or thinking of it in physics terms will make a little more sense. Okay. Now just like we were talking before, you can't power up units at a junction or a node. Whatever comes in has to go out. That's the same as this first law here. What we were doing in the earlier example, that's the first law here. Okay. Here's the difference though. In any path that you might have in closed path in an electrical circuit, and they've got to be closed or else they don't work. Okay. Any path in an electrical circuit, what your IR is a voltage drop. Okay. I thought I put an extra space in there. I is a current, R is a resistance. From Ohm's law, we know that's voltage. That's a voltage drop because that's the current flowing through a resistance, meeting the resistance. You have a voltage drop there, I times R. So the sum of all the voltage drops around a closed path has to equal to the total voltage source in the path. Okay, so if you have a battery or some sort of power supply or something in the path, that's a positive voltage. All the drops are negative voltages, and the sum of all your voltage drops have to equal your voltage supply. because you can't power up voltage in a given pathway. You have to, the net voltage has to be 0. Just like you can't power up current at the junctions, the net current flowing in and out of a junction has to be 0. Okay, so one is voltage, one is current. Okay, so let's do example 6. I think we're going to need the room, so I'm going to clear this. Is it all right for me to clear these two of Kirchhoff's laws? Now, actually, because they're showing up here, you can use who in the world was Kirchhoff? How did he come up with these laws? That's not exactly linear algebra, but guess what? It shows up in the book, so you could use those as paper topics. Okay, so unless there's some objection, I'm going to clear those two out of the way. We'll restate them several times, but let me draw your circuit. Okay, now, not going to be pretty, but let's get it done best I can. Here we have a circuit. I'll start at this point here. Oh, in the wrong mode here. Okay, draw mode. Here we are. We'll start at this point right here and go over here and hit a resistor. Okay, go a little bit further here and we hit a battery symbol. Okay, go a little bit further here and we take a right-hand turn. Right here we have node or junction 2. Coming down from your starting point here, we have node or junction 1. And coming out of 1, we hit another resistor. Okay, and that goes all the way to node or junction 2. Leaving junction 1, we go down and over, hit another resistor here, and hit another battery here, and comes up and that hits into junction 2. Now let me fill in the blanks here. They're calling this current 1 that's flowing through this resistor. I'm going to label it over here. And they have it going, and I'll explain in a minute why. In this direction, there's current 1, I1. This is resistor 1, R1, and they have that equal 3 ohms. This is battery 1, and they have this as being 7 volts. Now here's why it's a pretty good safe guess that the current would be flowing in this direction, because in physics we assume the classical current, the conventional current, goes from high potential to low potential. This is your high potential size of that battery, so that meaning this is the plus side. We assume the current flows from positive to negative. So that's why they labeled it here. Of course, if we were talking about electron current, it has to go in the opposite direction because electrons are negative, not positive. So we're going to use conventional current. Okay. Down here we have resistor 2. Let me get my pen to show back up somewhere here. There it is. Here's resistor 2. And resistor 2 is 2 ohm resistor. Alright, down here we have resistor 3, and resistor 3 is a 4 ohm resistor. Ohm is a unit for measuring this, and this is our battery 2, which we're going to say is 8 volts. By the way, I didn't draw in the other currents. I2 we're assuming is flowing in this direction, and I3 we're assuming is flowing back to the left again. Get out of there. This is so aggravating. Okay. This is I3 in this direction. Now the reason that makes sense is here's the 8 volts, there's the high potential side, the low potential side, so we assume the current is going to flow in that way. And if these two are both coming into junction 1, that one better be going out of junction 1. You couldn't have all three coming in. So I2 was then going in the opposite direction. Okay, so what we're ready to do now is Kirchhoff's laws. His two junction laws tell us this: I1 plus I3, or let's do it this way, I1 minus I2 plus I3 has to equal 0, because the sum of the currents coming or going from a junction has to equal 0. So let's state that again. I1 minus I2, because that's going out, plus I3 is equal to 0. Okay, now if we did junction 2 here, we would have minus I1, because this I1 is still going in that direction. Current can't change, I mean it's the same, so this would be minus I1 plus I2, because this would still be coming in like this, and this would still be going out like this. That would say I1, or minus I1 plus I2 minus I3 is equal to 0. That's that same equation. You just put a minus here, a plus here, and a minus there. It's the same equation. So that gives us no new information. So we only got what we needed from that first node or junction. We could have used the second one, not the first one, but we can't use them both because those are identical, basically, just opposite sign. Okay, my phone's ringing downstairs, but it can ring on. Okay, now let's do his loop law. This was the second law, and since we have the currents flowing in this direction inside here, let's use that loop law. Okay, now I'm going to put the voltage drops on the left hand side as positive amounts, and the voltage increase, the jump, that's what the battery gives you, increase in voltage, on the right hand side. So both of these will be positive. These will be the drops in voltage. This will be the rise in voltage, if I could get my thing to show up here. Then those would have to equal each other. So let's do this one. IR, this is I1 times R1, that would be 3I1. So there's 3I1. And down here we've got plus 2I2. Okay, is equal to 7. Okay, because that's the voltage increase, these are voltage decreases, they have to equal each other in loop 1. So I'm just going to call this loop 1. Down here we're going to do the same thing, but have loop 2 going in this direction. Okay, my positive voltage here is going to be 8, so I'm going to go and write that on this side. That's 8 here. And then what we have here is 2I2, and what we have here is plus 4I3. Okay, so there's our second loop. This is loop 2. And that's all we need. Okay, you could do another loop, the outer loop, but that would just duplicate what you already have. One of those would have to be minus and one plus. Well, let's not even go there. This will work pretty nicely for us. One thing to note, in this third equation, everything's multiplied by even numbers. So let's make this I2 plus 2I3 is equal to 4. Just divide everything by 2. Okay, and that should give it to us. Excuse me just a minute. I'm going to have to get something else to drink. My throat's getting really dry. All right, let's now do our matrix. Okay. Okay, the first one's a 1, minus 1, 1, 0. Augmented matrix here. Second one, 3, 2, 0, 7. Third one, 0, 1, 2, 4. I've already divided by 2. All right. Now what we want is a 1 here, and we want zeros below it, but I know coming up I'm going to want a 1 as my leading in the second row, so I want to swap these two rows. I want to just swap them. That's one of the legal operations we can do. Let's just exchange those two rows, and that becomes 1 minus 1, 1, 0, 0, 1, 2, 4, and 3, 2, 0, 7. Exchanging those top two rows. Now we've got a 1 here, 0 below it. We want that to become a 0, so to make that happen, it's minus 3 times row 1 plus row 3. All right, we're using row 1, so write it down. 1 minus 1, 1, 0. We aren't messing with row 2 now, so write it down. 0, 1, 2, 4. That's that new row 2. Now let's do this operation here. Minus 3 times 1 is minus 3 plus 3 is 0, exactly like what we wanted. Minus 3 times minus 1 is plus 3, plus 2 would be 5 down here. This will be a minus 3 plus 0 would be a minus 3, and that's a 0 plus 7 is 7. All right. Goodness gracious. Hold on a moment. Sorry. Hard to breathe. All right, now the question is Gauss or Gauss-Jordan? Do you have a preference? Anybody? We did Gauss last time. Let's do Gauss-Jordan this time. Okay, Gauss-Jordan, we wanted a 1 here, 0 is below it. We got it. We start Gauss the same way. We want the leading non-zero entry here to be a 1. We got it. We got that by exchanging the two rows. For Gauss-Jordan, we want a 0 above it and below it. So let's take care of this one. It's going to be simply row 2, if I could get my stinking pen to write. Row 2 plus row 1. So we're using row 2, so let's write down our row 2. And that's the 0, 1, 2, 4. All right, so adding the two rows together, 0 plus 1 is 1. 1 minus 1 is 0. 1 and 2 are 3. And 4 and 0 is 4. All right. Next, we want this 5 to become a 0. Okay, you got 1 here, 0 is below. 1 here, now we got a 0 above. We want a 0 below. How do we get that to happen? Minus 5 times row 2 plus row 3. And that should do it. So minus 5 times 0 is 0 plus 0 is 0. That stays the same. Minus 5 times 1 is minus 5 plus 5 is 0. That's good. That's what we wanted. And then we got a minus 5 times 2 would be a minus 10. Minus 3 would be a minus 13. I'm not looking liking the looks of that at all. And minus 5 times 4 is minus 20, plus 7 is plus 13. No, minus 13 again. Now it doesn't look too bad because we can row 3 divided by negative 13 is the new row 3. So this becomes a 1 and a 1. Is it okay for me to just erase that and make it happen? Any objection to that? I heard none, so I'm just going to erase my my minus sign in 3, minus sign in 3, and there we have it, 1, 1. Okay. Now, if we're doing Gauss-Jordan, we got our leading 1 there. We got that by dividing by minus 13. Now we want zeros above it. So the next step would be and by the way, we already know our first answer. I3 has got to be 1. Looks like it anyway. Okay. Now, using that row, we want this. We have a leading 1 here, zeros below it. Leading 1 here, zeros above and below. Leading 1 here, but we don't have zeros above it. So we want that 3 to become a 0. So it's minus 3 times row 3, and add that to row 1. All right, let's do it. Minus 3 times 0 is 0, plus 1 is 1. That should stay the same, and it did. Minus 3 times 0 is 0, plus 0 is 0. We wanted that to stay the same. It did. Minus 3 times 1 is minus 3 plus 3. That's a 0, which is exactly what we wanted. And then we have a minus 3 times 1 is minus 3 plus 4 is 1. So, current 1 also looks like it's got to be 1. Okay? Now, last thing, we have leading 1, 0. We want that to become a 0, so we're going to do minus 2 times row 3, minus 2 row 3 plus row 2. Let's do it to it. Minus 2 times 0 is 0, plus 0 is 0. Fantastic. We didn't want that to change. Minus 2 times 0 is 0, plus 1 is 1. We didn't want that to change. And minus 2 times 1 is 0, plus 0. Plus 2. I'm sorry, I can't talk. Minus 2 times 1, minus 2 plus 2 is 0. Oh, man. And then minus 2 times row 3 would be a minus 2 plus 4 is plus 2. So it looks like to me that I1 has got to be 1, I2 has got to be 2, and I3 has got to be 3. 1. What am I saying? I'm just getting carried away. I think I need to stop and get something else to drink. Okay, that's a 1. I don't know what it looks like, but it's a 1. All right, sorry. This is now. Let's see. Oh, and by the way, current is measured in amps. So to be correct physically, if I can find my pen, there it is. That would be 1 amp, 2 amps, and 1 amp. Now, if you ever come up with a negative amperage, that means you had your arrow in the wrong direction up here, but ours worked. Let's just see. 1 coming in from above plus 1 coming in from below is 2. 2's going out. That makes sense. Okay? Let's do your voltage here. You went up 7 volts. Here you dropped 3 volts. 1 times 3 is 3. You dropped another 2 times 2 is 4. That would be dropping 3, dropping 4. That's dropping 7, adding 7. That comes up to 0. Down here you had plus 8 minus 4, because your current here was 1. Minus 4, that gave you 4, and plus 4 here would be 8 again, or minus 4 here would be 8 again. So sure enough, those work. Let's make sure they did it correctly on theirs. 1 amp, 2 amps, 1 amp. Very good. There was Kirchhoff's law, analysis of electrical network. Now, example 7, even bigger network. Not really, yeah, it is a bigger network. So can I leave it? Can I clear it? Any questions on this before I get rid of it? Everybody see what we did? All right, let's clear the drawing and make us a new drawing here. This is fairly intricate, so let's get it going here. Whoa. We'll start at this node up here. Not node. Yuck. All right, let's try again. Start at this corner up here. It's not really a corner, but that's how we draw it. Start here and go across here until we get to junction 2. Keep going across here until we get to junction 4. Keep going across here and we have a corner. Go down here and we have 14 volt with the big side up. 14 volts in that direction with a 4 ohm resistor. Take a corner here, hit another junction here, 3, go up from 3, hit another resistor here. That makes its way to 4. This is a 2 ohm resistor. Okay. Come across from 3 to 1. And you ran into a 1 ohm resistor. Going up from 1 to 2. You hit a 4 ohm resistor. My drawing really stinks, but you're used to that, aren't you? And then going here from 1 and going north from there, we hit a resistor, and that's a 2 ohm resistor. And then we go on up and hit a 10 volt battery in place in that direction, going down like that. Okay, I think I've got my drawing in place. No, I don't. What in the world was I thinking here? Okay. All right. I had my junction here, but I didn't have this in place. We have a 17 volt battery here, and we have a 2 ohm resistor here. Okay, should have a total of 6 resistors. 1, 2, 3, 4, 5, 6 resistors. 3 power supplies or batteries. Got them. And we've got 4 nodes. I think we're okay. Now, this is going to be harder to tell what's what because there's so many moving parts. So I guess junction law should be first. Let's first draw our currents. We have a current going downhill here, and that's the one thing I forgot to get off my drawing. What did they name this one? They named this current I1. Come on, pen, where are you? There you are. This is I1 here. Now, if I1's going down like this, there's a good bet that I2 is going uphill here, and it is. So we'll put I2 here. Okay. I3 is the one down here, and I'm guessing it's flowing, yeah, in this direction here. So this will be I3 flowing in that direction. I4 over here, that's the one up here top, and I'm guessing that's flowing in this direction, I4. Let's see if that's how they have it. Yes, that's how they have it. I5 is the one here, and I'm pretty sure it has to be going downhill. I5 here. Let's see if that's how they drew it. Yes, it is. And then I6 is the one over here, and I'm pretty sure that's going in that direction. Let's see if it is. Yeah, they draw it in that direction. Okay, now I finished my drawing. Now, let's talk about the junction laws. Start with junction 1. You got I1 coming in, I3's coming in, and I2's going out. So let's say this is I1, because that's coming in, minus I2, that's going out, plus I3, that's coming in, and then you have that has to equal 0, because the sum of the currents coming in and out have to equal 0. Okay, junction 2. Okay, you got I2 coming in, I1 going out, and I3 going out. So let's have our going outs to be positive, coming in negative. So again, you got an I1 here. I don't know. Let's make that negative. Minus I1 here, because that's going out. So help me remember that. Plus I2 and minus I4. And that's equal to 0. Oh man, 3 minutes. Yeah, we're fat chance we're going to finish this one. I3 down here. I mean, node 3. We've got I3 going out, I5 coming in, and I6 going out. So let's make the I3 here positive. Minus I5 and plus I6, have that equal 0. It's not totally arbitrary, but I just chose I1 to be positive, so therefore I6 had to be positive, I5 has to be negative. Junction 4. Okay, we have an I4 up here coming in, so let's have that positive. I4 minus I5 plus I6, and that has to be 0. Those are our 4 junction laws. I doubt if all 4 of those are linearly independent. We'll worry about that later. Now, let's get some loop laws. Okay, the loop law here, it looks pretty obvious. One loop could easily be this one. So this will be loop 1. This one I think I would do in this direction, and this would be loop 2, and this one I think would fit pretty well going in that direction, loop 3. Okay, now loop 1, we have a positive 10 here, so that's an increase. So let's put our voltage drops on the right hand side as positive. This is 2I1 plus 4I2 and that's equal to 10. The voltage drops on the left hand side, the voltage increases on the right hand side, they've got to be equal each other. We are out of time. Let me just write these down pretty quickly if I can. You got 17 over here is your voltage in the second loop, and here we have a 2I4 here we have a 2I5 and here we have an I3 here. So those are, oops, and then we have a 4I2 here. All right, these are our voltage drops around that loop. Voltage increases that one. And the last one here, we'll have a 14 over here on this side. And on this side we have a 2I5 plus 4I6. Which makes me think I messed up something here. No, that's fine. I think that's fine. So there. We have 6 unknowns, 7 equations. One of these has got to be redundant. And we'll find that out later. We don't have time for it now, but we'll pick up with this. Those are our equations. So we'll pick up with that and go to the augmented matrix next time. So let me put my arrow in the right place here. I put arrows to tell me where to start, but I have them from previous terms here too. So we're going to start from going from that to that. Okay, now that's done. Let's see about homework exercises. We came back close to finishing, okay, but didn't quite finish. Homework exercises here. You can do any of the odds 1 through 11 that you want to. We didn't do polynomial curve fitting, but if you think that's something you might be doing in the future, it's certainly doable. It was all given in the book. 13, also you could do that if you'd like. That should be a fairly easy one. Number 15, and all these are at Calc Chat. Their answers are in the back, but also worked out solutions at Calc Chat. 17, or let's see, any of the odds 17, well 17 or 19. They're more similar to what we had before. One's population, one's net profit. Then beginning with network analysis, you certainly should be able to do these because we've done them. Either 21 or 23 are the network analysis like we did with the previous example, and you can start working on 25 or 27 if you would like. Okay, we didn't do one like 29. We'll hold off of that. They aren't going to have any in the book like it, so you can start working on those if you want to. If you can't figure them out, we will work those in class, so let me know. Partial fraction decomposition, we've done that in Cal 2 or 3, depending on which one you were in. That's 31 or 33. In calculus, 35 is one that you might run into there, eigenvalue problem. Similar, 37, 39, and 41. You can do try any of those you want. That's completely up to you. We'll stop there, talk about finishing up later. Now, I'm pretty sure that I put the first test out there for you on Blackboard Message. Okay, have any of you seen that first test? Nobody? I think I put it out there. Okay. Yeah, it's Blackboard Message that you don't officially, the clock doesn't start on that until after Thursday. But you got time to get started if you wanted to. I said I would give it to you so you could use the holiday weekend if you wanted to, but it's over with, but you still get an extra couple days on that. Of course, you can take all the time you need, just don't have it running into the second test. So first test is out there. You can get started on it. We'll go over additional problems that you might find helpful later. Okay? Any questions, last thoughts, parting shots, anything before I stop sharing? Okay. Let me just make sure that my equations are the same as theirs. I didn't think to look at that. I1 minus I2, yep, I2. Okay, they did it slightly differently, but it's okay. I3 minus, yeah, that's fine. Yeah, that looks right. 2, 4, 10. 4, 1, 2, 2, 17, 3, 4, 14. Yeah, we'll start with there and pick up and go from that next time. All right, good deal. Any questions? Okay, well, I'm sick and tired of sharing, so I'm going to stop the sharing. And unless you have any last thoughts or parting shots, I'm going to end the meeting for all of us. Okay, I hear none, so take it easy. We'll see you on Thursday, 11:30, right? Take care. Bye-bye.